me to do it after class? All right, let's get started. So any questions about anything? So I, oh,
On the lab, there was one section that I can show it to you after class.
okay,
It was a little confusing from the video.
okay. Yeah, so I still need to put in all your grades. Your lab should be graded on Gradescope, but I haven't transferred everything over to Blackboard, so that should be happening soon. And then other than that, just get in any remaining assignments that are missing. And so just as a reminder, so your final, if you're in person, will be 4 p.m. on Thursday. And otherwise, if you are taking it online, then the exam will open on Gradescope on Thursday, unless you've made alternate arrangements. All right, so let's just go through the exam, do similar questions. And so we'll do number 1. So calculate the heat in kilojoules when 5.92 times 10 to the third grams of NO2 are generated. And you're also given this equation, 2NO plus O2 gives you 2NO2, and the delta enthalpy of this reaction is negative 114.6 kilojoules per mole.
evolve?
Yeah. So do we have answer or anything, or how should we start? What should we do?
NO2AC?
Are generated.
Oh, are generated. Okay. Okay, there we go. That makes more sense.
So what should we do first here?
Find how many moles it is.
So let's do that. So we'll set up 5.92 times 10 to the third grams. And then, what's the molecular weight for NO2? What did you say?
46 point.
So 46.001. So we said let's divide, so 1 mole NO2, 46.001 grams. And then, so, oh, 0.005. Doesn't matter too much. And so what do we go from here? So this would give us, I'll just put in parentheses, right? So now we have moles of NO2. That's where we're at. The 46.005. So then we're given this piece of information. So what should we do with this? Because we're trying to get heat. Because we're almost there, right? Because we have moles of NO2. And then just think about what this expression is really telling us. It's telling us when we generate 2 moles of nitrogen dioxide, that it evolves this much heat, right? So it's giving us a kind of moles to heat ratio. So we kind of have something that we generate. Let me rewrite this. We generate negative 114.6 kilojoules of heat for these 2 moles of NO2. So then we can just treat this as like our conversion factor and then plug this in for just the last bit. So now we have moles we want to figure out how many we'll get. We know that 2 moles generates this much heat. And so there's our 2 moles of NO2. So you see how moles of NO2 is going to go ahead and cancel. And then that will just leave us with kilojoules. And so now we just have to plug everything in. So 5.92 times 10 to the 3rd divided by the molecular weight of NO2. Oops. And take that times our negative 114.6 and then divide it by 2. And so do we get this for our answer? Thumbs up, thumbs down. I don't think there's anyone in the chat today. So then negative 7,300, let's see, so we're given 3 sig figs. So 7,370 kilojoules of heat. All right, let's do the next question. So express the equilibrium constant for the following reaction. So A2, B5 plus AB gives you 3XY2, or sorry, AB. And then these are all in the gas phase. Do we have an answer for this one?
Is it AB6/E2V5?
No. So you have products over reactants at least. Let's start with that. And it seems like you were like kind of going for the right idea. but instead of multiplying it, what do we need to do to the 3 there? So we have to take it to that power. And since it's concentration, you don't want to do like any other things. You just want to do AB, so this is like your molecule to the 3rd. And then over A2B5. And then that's just to the power of 1, since a coefficient of 1. And then times AB. So pretty close.
Why do we have to go to the power again?
That's just part of the expression where it's raised to the power of the coefficient.
Okay.
Since it would, on the rate, it would go up by that many amounts. Like if you take one molecule and then you increase it, right, but then it's going into 3 different things and it's increasing like exponentially.
Oh, okay, that makes more sense.
All right, good on these. Just raise them to whatever power. So then next one. So a water sample contains heavy metal mercury with a concentration of 10 parts per billion, and that's by mass. And so what volume of water has 100 milligrams of mercury then? And you're given a hint that the density of water is just 1 gram per milliliter. So how do we start this?
Oh, that'll be a lot.
Bless you. So what was parts per billion? What's another way of expressing it?
1/100 million?
So we could do 1/100 million, or 10/1 times 10 to the 9th. Any other ways of expressing it?
One, 2 times 10, or 10. No, 1 times 10 to the negative 10, because,
So I'm looking for like a different sort of relationship,
uh,
maybe some units of something. So parts per billion can also be micrograms per kilogram. And so I like this expression just because it's easier, at least for me to wrap my head around it. Because now we can just write, okay, now we have 10 micrograms for every 1 kilogram. And so we could set up a proportion basically. So we want 100 milligrams. So what's 100 milligrams in micrograms? So what's micro's factor?
isn't it a factor of 8?
No. Yeah, so 10 to the negative 6.
Oh, right.
And then milli is what?
Oh, right, 3. -3.
Yeah, so 10 to the negative 3. So we could set up our conversions. We could do it longhand, just so everyone is on the same page. So let's just kind of do an aside. So how many milligrams? I'm going to go milligrams to micrograms. So 100 milligrams. If you don't want to find the factor between the two, I would just do the two-step conversion. So milligrams to grams. So there's 1 times 10 to the 3rd milligrams and 1 gram. Then grams back to micrograms. So there's 1 times 10 to the 6 micrograms in a gram. And so then you can see you're just multiplying by 10 to the 3rd. So then you have 1, 2, 3, or 1 times 10 to the 5th. So that's how many grams of mercury we're looking for. And so I think the easiest thing to do would then just be to set up a proportion. So now we have 10 micrograms over 1 kilogram is equal to 1 times 10 to the 5th micrograms. And so over x. So then we have to solve for kilograms. So 1 times 10 to the 5th, and then times 1. So you're just cross multiplying, and then divided by the 10. And so then you would get this. So 1 times 10 to the 1, 2, 3, 4. So kilograms of water. And so kilogram is just the same thing as liters. So 1 times 10 to the 4th liters of water. So does that make sense?
What's the difference between kg, kilograms and the H2O?
Of, so no questions on this one? So let's do some stoichiometry. So a chemist reacts 20 grams of silicon dioxide with 40 grams of HF. And so you're given this formula of silicon dioxide plus HF, sorry, 4 equivalents of HF gives you silicon tetrafluoride plus 2 equivalents of water. And so the question is, so what is the limiting reagent? And then what is also the theoretical yield? So I'll give everyone a few minutes to get started. Did we get to an answer yet? So let's see how it's going. So what's our first step? So finding moles. Let me see with this pen. Yeah. So you want to do silicon dioxide first? Okay, so let's just do that. So we'll start with our silicon dioxide. And so we have 20.00 grams of it. And then we want to find, so what's the molecular weight of silicon dioxide?
60.086.
So 60.086. So then we'll divide. So 1 mole of silicon dioxide is 60.086 grams. So then grams cancels. That leaves us with moles of silicon dioxide. And then, so what do we do after that?
Mole-to-mole ratio, is it 4 HF for 1 SiO2? Or do you
So-
do the product?
So you could do either one. In this case, I think it'd be easier if you did the product. So it wouldn't be wrong if you had done it with the HF, and then you see, like, do I have enough HF or excess HF? So that's one way to do it. But I'll just do the silicon tetrafluoride, since that's the product we're most interested in. And that's also how we can get our yield. And so what's our ratio in this case? So 1 to 1. So 1 mole. And so I'm going to put silicon tetrafluoride on top, silicon dioxide on bottom. So that cancels. And if we wanted, so we could stop here. This would give us our answer. And then the last step, we just have to multiply the molecular weight of silicon tetrafluoride. But we could leave that till the end after we find our limiting reagent. Or you could go ahead and put it in grams. It doesn't really matter. So what's the molecular weight of silicon tetrafluoride?
47.084.
That sounds low. You said 47?
Yeah, I didn't do 4x.
Oh, okay. So 103.67. Is that what other people got? Something similar? Sounds about right. And so I'm going to go ahead and just plug in this for a second. So we have 20 divided by our 60.086. So now that gives us moles of silicon dioxide. So they're at a 1-to-1 ratio. So we can either stop here and say that we have 0.33, almost rounded to 3 moles of silicon tetrafluoride. Or you could go on. See if I can do this. And so if we're here and just go on and convert to grams, so then we can just multiply it by our molecular weight, so 103.67. And so that'd be grams for every 1 mole of silicon tetrafluoride. So we'll put both answers, 1 and 3. So now it looks like that's 34.5 grams. And so now let's compare this answer to what happens with our 40 grams of HF. So now just repeat the same process, except now we're going to plug in, so 40 grams for HF, and then what's the molecular weight of HF, like 20?
20.006.
20.006, so 1 mole of HF. And then, so what's our new mole ratio?
2 more.
If we're doing, so let's do HF and silicon tetrafluoride. So what's the ratio?
1 to 4.
So 1 to 4. So our 4 moles of HF goes on bottom to cancel out 1 mole of silicon tetrafluoride on top. So then here's where you could kind of stop and compare, or you could go on to calculate the mass. And that'd be the same step. We'll take an aside here. So 40 divided by 20 divided by 4. And so I get 0.5 moles of product of silicon tetrafluoride, and then we could convert this to grams. So that'd be 51.8 grams. And so either way you went, so which one's our limiting reagent? Zoom out so you can see. So silicon dioxide, exactly. So there were less of it, so that is the one that's going to stop the reaction. And so if you had left it in moles, you could, of course, go ahead and multiply by your molecular weight to give you your grams for your answer here. Any questions on that one? And just show your work. You know, it's fine if you don't show your work like this, but just label everything step by step then, so I can see, like, I calculated, you know, this many moles and then I did this step, just so I can, you know, at least follow your train of thought and then give you the most points as possible. Because it's easy, you know, to somehow plug in the wrong molecular weight or something, but as long as I can follow it, I can be generous. All right, so now let's try another one. So a sample of xenon gas is in a container with a volume of 10.8 liters at a temperature of 112 degrees Celsius with a pressure of 5.11 ATM. So how many moles of gas are present? So do we have an answer for this one? Or what equation do we need? Let's start with that. What's our good old equation for this type of problem?
Is it N equals PV over RT?
Yeah, exactly. So you gave it to us fancy. So N equals PV over RT. So that's already the solve for you form. There's also PV equals nRT. So I would have that written somewhere. So excellent for rearranging it. And so now all we have to do is plug everything in with the right values. And so looking, volume's already in liters, so that's good. Temperature we need to convert to Kelvin. Now we have to do 112 plus 273.
0.15.
So I usually leave off the 0.15.
Heresy. That's like
I know.
half a degree Fahrenheit.
Yeah, but as long as the problem doesn't say like exactly 0 degrees, then I usually just leave it off. But you can put it on there if it makes you happy. I don't want to deprive you of that. And so pressures already in ATM, and then do we remember what the gas constant was?
It was, I believe, 0.08. No, 0.26, or was it 0.206? It was one of the two.
What is it? 0.21? All right,
They're ready to.
perfect. And so now we can plug it in. So, like we have everything, so N. Now I'm just plugging in everything, so pressure, volume, gas constant, and our 385. And so what do we get for N?
1.74.
Is that what other people got?
10.82.
Somebody's off by a factor of 10. So I got the 1 point, you said, is that what you got, 1.7? So I'll round it to 1.76. So I would just double check that you plugged everything in right, parentheses, matter, or you could do divide. So N equals 1.75 moles. All right, let's do another gas one, and then the last one should go quick, hopefully. And you'll have plenty of time for the exam. Obviously, we're doing the whole exam in a shorter period. And so we have the initial volume of gas at 2.3 ATM is 9.2 liters. So what is the volume if the new pressure is 4 ATM? Do you have an answer?
Yeah, would it be 5.29 liters?
Let's see, so 5.29 question mark. So what equation did you use?
What was it called again? Oh, right, it was, P2 equals, or no, sorry, volume 2. Volume 2 equals V1 times P1 over V2.
Yep. But there's also, so don't forget, you can take this PV equals nRT and turn it into, so set it to R, gives you PV over NT, which gave you that super form. So that way you don't have to remember anything. These things cancel, leaving you with P1V1 equals P2V2. So then you just rearrange. So that looks good. Except I plugged in something wrong. Oh. P2, I just wrote V2 instead.
I think I said the wrong one.
Yeah.
Wait, no, because it was, we're trying to find volume two. No, never mind, that makes sense. I was
Yeah.
just trying to remember which variable stood for what again. That's why I was blanking. I did the thing, I knew the formula, I'm just like, wait, no, not T, it's temperature. Temperature doesn't change for this. That would mess everything up.
So 2.3 times 9.2 divided by 4. And so, yep, I like the answer of 5.29 liters. All right, so now let's kind of switch to molarity and all that. So what is the molarity if we dissolve 37.9 grams of hydrobromic acid in 1,000, yeah, we'll do 1,200 milliliters of water. So what's the formula for molarity again?
The grams over liters.
So I think,
Grams of the salt.
no.
Moles of salt over liters of solution.
Yeah, so moles over liters. And so then what's my problem with the 37.9 grams? So what do we need to convert grams to? So moles. And so let's do that. So 37.9 grams. And then what's the molecular weight of HBr? 80.912. So then that should give you about 0.468 moles. And then we need to convert milliliters to liters. So how many liters is this? 1.2 liters, and now we just have to plug that in. So 0.468 moles divided by the 1.2 liters. And you could have done it in the dimensional analysis form. I just did not. So divided by 1.2, so then that gives us 0.39 molarity. So any questions about that one? Hopefully these are easier. So if you dilute (20 milliliters) of a 12.0 molar HCl solution to make let's do 3 to make 3.15 molar HCl solution. What is the final volume?
Be about 76.2?
Let's see, I haven't calculated. Is that what other people got? So sounds right if we got a consensus. So 76.2, and then was that milliliters or liters?
That's milliliters. So if I want that in liters, have
So-
to move the decimal over a couple places to 0.0.
And so just to go over it for everybody, so C1V1 equals C2V2, or molarity. And then we can just plug in all our values, our concentration, 12, times our volume, and I'm just going to keep it in milliliters, equals 3.15 molarity. And so now we're solving for liters. And I'll just punch it in, even though, since we have a consensus, sounds pretty good. And so now we verified it, so 76.2 milliliters. And last question on your exam. So calculate the pH of a 1 times 10, oh, let's not choose that number, actually, that's boring. Sorry. sorry, of a 6.43 times 10 to the negative third molarity solution of HCl. So do we remember the formula for this one?
I say purple. No, we already did purple.
I know it.
Blue color. Cyan, yeah, that color works.
Which one?
The one you had selected.
This one? I don't know which one I selected. The only thing that it slightly upsets me about this full version, because there's like 2 different versions of OneNote, right? And so I have to use like what's called the full desktop version. But the app version comes with cooler pens. Like there's a rainbow pen, there's like a galaxy pen.
I'm sure you just haven't figured out how to use them.
There's this BS.
Yeah, maybe I could see if I can try to like install it. I don't know. That's my summer
Wait,
project.
no, click over where like the pre-made pens are, because it would probably be under pre-made, wouldn't it?
Where?
Like the era over there, next to color and thickness. To the left of it, wouldn't it be under there?
See, it doesn't have any of the cool ones though built in.
Can you scroll at all, or no, it's at the bottom?
No. And that just goes into other things. Oh well.
That's sad.
Yeah, it makes me sad because I want like cool
Just
galaxy.
do it by hand.
Yeah, because I could change like colors as I write. That'd be cool. But I can barely write as is, as you can tell.
Just make a hotkey or something.
Yeah, I'll figure it
Set
out
up a
maybe.
macro.
So what's our formula?
Is that the pH equals pKa thing?
So that would be like for a buffer. But what if we just have a regular? So this is just a regular strong acid.
H equals negative LOG times
And so, yeah, so negative log of the hydrogen concentration. And so in this case, right, we have HCl. We know it splits into hydrogen plus chlorine. And so this is the same thing as the H plus concentration then for a strong acid. So all we have to do is plug in this number into the log. And see what our calculator spits out at us. So negative log of 6.43 times 10 to the negative third. And so we should get a pH of 2.19. And definitely make sure you plug that in, test it out, because just in case your calculator is like not in base 10 for log or something weird. So just make sure your calculator is functioning.
It's in base 27.
You never know. All right, so that is the exam. We went over every question. All I did was change a few numbers or variables. So if you felt good about this review, then you should be good for the exam. And then I don't think anybody's online, but I'll hang around for questions. And of course, I think people in class wanted to ask me questions, so you can take all those. So thanks again for class, and I'll see y'all 4 p.m. on Thursday. Otherwise, you're made arrangements with me.